So today is day 18 and we will be covering Dijkstra algorithm. Now what is the definition of this Dijkstra algorithm? Basically this is the algorithm that is used to find the shortest path from a source node to all other nodes in the weighted non-negative graph, right? Now what is weighted non-negative graph? Let's make a graph. We are having, let's say, nodes 0, 1, 2 and 3 and 4, right? These are the 5 nodes. Now we are having the edges between them, right? These are the edges. Okay, now these should be the non-negative edges, means they will be having some weight, right? Weighted and non-negative edges. Let's say from 0 to 1 we are having weight 2. Okay, this is non-negative and weighted. From 1 to 2, let's say 1, let's say 4, let's say 7, and here let's say 1, let's say 3. So this is the weighted and non-negative graph, correct? This will be the example. Now what does this Dijkstra algorithm says? It says we need to find the shortest path from the source node to all other nodes. Okay, so let's say the 0 is the source node. Now we will be finding the distance from this to all other nodes, and the distance should be the shortest. Okay, so let's say we are maintaining the distance array of what? Of the distance from source to all other nodes, right? All other nodes. So let's say distance array is like this: 0, 1, 2, 3 and 4. 0, 1, 2, 3 and 4. Okay, now this is the distance array which will show the distance from the source to that node. Let's say we are getting the distance of 1. It will tell us the distance from 0 to 1 node. Same with 2, distance of 2. It will tell us the distance from 0 to 2, right? And other nodes, other index we can say. Okay, now from 0 to 0, the distance will be 0, right? It will be 0. From source to source, the distance will be 0, correct? This is the prerequisite, we can say. Okay, the base case. What else? From 0 to 1, what is the shortest distance? It's 2, right? We can say 2. And from 0 to 2, see, one distance is this one, right? 1 we can grow directly to the second node. The distance will be 4, right? 4. Now the other way is we can go via 1. We can go via this route. Here the distance will be 2 plus 1, that is 3, correct? So what is the minimum? Minimum is the 3. So we can write it 3 here because we need to find the shortest distance, correct? Now second is done. We got the shortest distance via 1, via this path. Okay, via this path. Now if we want to check for 4, from where we will go? Either we can go to this path, right, like this, via 2, but this will be the greatest. Why? Because 2 itself is having the greatest distance. For the 2 we are having the smallest 3. So we will go via this path, right? We will go via this path only. We will get the distance as 6, correct? Now for 3, again we will go with the shortest distance only. We are having this path also, right? This path also, we will calculate it. It's 11, yes, 11. From here it's 2 plus 1 plus 3 plus 1, correct? What is the sum? It's 7. So shortest is 7 only, right? So this will be the distance array. We will be returning this distance array. Now if someone asks you, like, let's say, give me the distance from source to node 3, we will simply return distance of 3. It will tell us the distance from the source to the third node. Okay, this is the basic flow of the Dijkstra algorithm. This is the basic definition of the Dijkstra algorithm, how this will work, and this is what we are finding. Now there are some key concepts. It will work only with the non-negative weights. This is important. Weights should be non-negative, right? So it should be positive. It should not be like -2 or -3. So this should be positive only, the weights. And it uses the greedy approach. At each time we will be picking up the shortest path. Okay, at each point, at each step, we will be picking up the shortest path. So this is the greedy approach, right? And we will be using the priority queue, that is the min heap. We already done this, right? Minimum heap that will maintain the order. Let's say if we want to pop out the element, it will give us the minimum element, correct? So we will be using this min heap. Now how we can do this? How we can do? I already explained this, right? The flow, how we can code it. Now we will be using the priority queue. Priority queue. Okay, queue. Let's see the step first. These are the steps working of the Dijkstra algorithm. First step is this one only, the base case, that is set distance source equal to 0. We already set it, okay. And other distances as infinite, okay, because if we later get a smallest distance, we can update it, right? The second point is push the source node into the min heap as a pair. This is important, as a pair. We will be using a pair. In the priority queue, we are using pairs, right? Let's say we will be pushing the pairs. Pair is what? Pair of distance and the node. Now what is this distance? This is the distance from the source, from source to the current node, to the current node, right? So we will be pushing this pair into the queue. Okay, so let's start with the first one. Okay, so first we have pushed what? Source code, right? The source node. Let's push it. What will be the pair? Distance is 0 only. Distance is 0. So the pair will be 0, 1. Node is 1. We will push it. Okay, let's push it here. 0, 1. Now what is the next step? Next step is pop out the element, pop out the top element. In the min heap, we will get the minimum distance, right? Now this is the min heap. We will be maintain min heap on what? On the distance parameter, right? Distance parameter, this one, right? So that we will get the shortest distance at first, right? So pop out the top element, and what else? We need to check for each of the neighbors of the current node. Okay, so second step is pop out. Okay, we have popped out, and check neighbors. Let's say we have popped this out. This is out now. Let's check it here. 0. This is what? This is the distance from the source till. This is also 0. Why I have written 1? This is 0 node, right? 0 node. Here also it's 0. This is 0 based nodes we are checking, right? Till the current node, correct? So this is the pair we popped out. Now we need to check the neighbors. What are the neighbors of 0? If you see here, what are the neighbors of this 0? Let's copy this. Now the neighbors of 0 are 1 and 2, right? We can write it as 1 and 2 are the neighbors. Okay, let's proceed with the 1. What is the distance now? We need to make the pair. Now for the pair, we need to calculate the distance. Let's take the fifth step here. For each adjacent neighbor of the current node, calculate the distance using the formula. What is the formula? Distance of V equal to distance of U plus weight. Correct. Weight between them, between U and V. Okay. Now let's say what was the distance here. It was the distance from the source till the current node, right? Let's say we are here and we need to calculate the distance for its adjacent node, that is 2, right? Now we can apply this formula, right? This is the v, so we can say distance of 2 is v, this is v, this is u. Distance of 1 plus weight between them, weight of u and v. Correct. So what is the distance of 2? We need to find it. What is the distance of 1? It's 2, right? Distance from the what? From the source till the current node. It's 2 plus the weight between them. It's 1. We got 3, right? So that is the distance, right? That is the distance from the source till the current node, right? We got the distance. So we can make a pair for this 3 and what else? The node, that is 2. Okay. This is the example of this formula. We can also apply it here. How? Let's see. So now we need to calculate the distance for this adjacent node, that is 1. Okay, let's apply the formula. So distance of 1 will be what? Distance of 0, right? The u, that is this node, correct? Plus the weight between them, weight of u and v. So what is the distance of 0? It's 0 only, correct? We have seen here, it's 0 only. Okay, and what else? What we need to add? The weight between them, that is 2. So we are having the value now 2, right? So we can say the distance of 1 from the source node is 2. Okay, is 2, 1. We got the pair. We can now push it in what? Heap. This will be the third step. Push neighbors pair in the what? Min heap, right? Okay, so we will push this in the min heap. Let's push it 2, 1, right? This is the new pair of the node 1. Okay, great. There will be one more thing. After applying this formula, we need to check one more thing. If the distance, that is this distance, the 2 is smaller than the current value of this distance, right? Distance of 1, it was infinite earlier, right? We will check if this 2 is smaller than the current value of distance 1, then only we will push it. Then only we will perform this third step. Okay, let's say I will explain you afterwards. Let's say for this example, I will come to this. Okay, so 1 is done, we pushed it. After that 2, again we will get the distance. For 2, what will be the distance now? It will be 2, it will be 0, right? And the weight between them, weight is what? Weight is 4, right? It's 4. So the total sum will be 4 only. Okay, now we got the value of distance 2 as 4. Now let's also maintain the distance array. Okay, distance array 0, 1, 2, 3, 4. We got the value for 0, it was 0 only, base case. For 1 we got 2, right? For 1 we got 2. For 2 we got 4. Right? Others are infinite only. Okay, now next we got the value 4, 2. We will push it. We will perform this third step. Let's push it in the queue 4, 2, right? Now this is the min heap. We will get the minimum first, right? That is this node. Now let's start with this 2, 1. Here everything is completed, right? All of the neighbors. Now we will again go to this part, the second part. Okay, pop out the smallest element, check the neighbors. We popped out this. We will check the neighbors for node 1. What are the neighbors? We are having 0. We are having 2, right? If you see here, for 1 we are having 0 and 2. Now 0 was already processed here, right? It was already processed here. We already popped this out and processed the neighbors. So we can say for 0 it's already done, so we are not processing it further. Why? See, we have returned the minimum value, right? If we are popping out from this, it will be the minimum value, right? Minimum distance we can say. So after this, everything will be the greater only. So every path will be the greater, right? To reaching this 0 node, everything will be the greater, correct? So this is the property of min heap. If we are popping out something, that means this is the minimum value to reach that node, correct? After that, anything will be there, will be the greater value only. Okay, so if we consider this here, I will show you the example here. Let's say we are considering this 0. Now what will be the distance? Let's apply this formula. Distance of 0 will be what? The distance of 1. Distance of 1 plus the weight between them. Distance of 1 was 2, right? 2. The weight between them is again 2. It will be 4, right? It's 4. So no need. We already have this distance 0. Why we will update it to 4, right? Why we will go with the greater path? So we will not exploring this. Okay. Kata, cross. So we will be maintaining some visited, and if we are popping out it, we will make this true. That means we already got the minimum possible value for the current node. We are not processing it further. Okay, right? So 0 we are not processing. For 2, let's start. We are having the neighbors. What are the neighbors? We are having not neighbors. First we need to check the distance and the node pair. So let's calculate the distance applying the same formula. Distance of 2 will be distance of 1 plus weight. It will be what? Distance of 1 is 2 plus weight between them is 1, right? So we can say it's 3, right? Distance of 2 is 3. So we can write it here. We can update it, right? We are having the value 4. 3 is smaller than the 4. That means we can update it here. Okay, 3. So we got the smallest value. Pair will be 3, 2. Let's push it here. So 3, 2, right? 3, 2. And we popped out this one, right? This was popped out. Now the next will be the smallest one, right? That is this one, 3, 2. Let's start with this. We are having the 3, 2. This is the smallest, right? So what are the neighbors for 2? For 2, we are having the neighbors 0 and 1 and 4 and 3. Okay, 0, 1, 3 and 4. Correct. 0 and 1 are already done. Yes, this is processed, visited, true. We are not processing it further because we already got the minimum value, minimum shortest path for these nodes 1 and 0. Okay, so you can try it by yourself. Okay, we will not be getting the minimum value from 2, correct? So 2, 0 and 1 is completed. Let's move to the 3 and 4. So let's start with the 3. What is the distance? Distance of 3 will be distance of 2, that is 3 plus the weight between them. Weight between them is what? Is 7. Let's update this 7. We got the sum 10. So we can say the distance from the source till node 3 is 10. Let's see in the distance formula, we are having infinite. So 10 is obviously shorter than the infinite. We will update this 10, right? So this is done. This is done. We will update the value 10, 3. We will push it here. Push it here. What is the value? 10, 3. Right? This is popped. What's next? The 4 is next. Right? Again, we will calculate the distance of 4 will be what? The distance of this 2, that is 3, plus the weight between them. What is the weight? It's 3. It's 3. Add it 6. Right? We got the distance of 4 as 6. Let's see in the distance array. We are having infinite. We need to update this, right? 6. So what we are doing basically? We are pushing it, and one more thing, we are checking checking what? If the calculated distance is smaller than the current distance value, then only update this and push it, right? Push it. So we can say this part here. Okay, before pushing the neighbor. Okay, after calculating sum, this will be the third point, calculating sum, and this will be the fourth point. We are checking, right? If the calculated distance is smaller than the current distance, then only we will update this and push this. That means we got the shorter path, and this will be the fifth. Got it? Okay, so these will be the things, and somewhere we will also be checking for the visited array. Visited should be false, then only we will checking out the neighbors for that. Okay, here some. After popping out, we will be checking if it's visited or not. If it's visited, then we will not proceeding with the neighbors. If it's not visited, then we will check the neighbors. The example of this is here, this one. Great. Now the new pair was here, was 6 and 4. Let's push it here, 6 and 4. Now what is the smallest value? This one, right? This one, 4 and 2, right? But 2 is already processed. We are not going with this, right? We are not going for this one. So let's check for the next one. Next one is 6, 4. This is the smallest, right? This one is the smallest. Let's check out this. So for the 4, what are the neighbors we are having? 2 we are having, and 3 we are having, correct? And 3 we are having. 2 is already processed. We are not going for this, and otherwise we can also go for this. We can have the if condition, like checking condition in the popping out code. Okay, I will explain you the code. Let's not take this case because this is already visited here. Okay, so let's check this third node. This is not processed yet, correct? So let's check the distance. Distance of 3 will be distance of 4, that is 6, plus the weight between 3 and 4. What is the weight? It's 1, right? So let's add it here. It's 1. Okay, so we got the distance of 3 as 7. Now let's check in the distance array what we are having. We are having 10, right? 7 is smaller, so we will update this, right? We are checking this condition. If the calculated distance is smaller than the current distance, then only update this, update the value of distance of 3 as 7 and push it. Now we will push the pair, that is 7, 3 in the priority queue. So 7, 3 in the priority queue. Let's add it here, 7, 3, right? Now let's move this out. 7, 3, this is the smallest. Again check the neighbors for the 3. We are having 2, we are having 4. Both are processed, right? So we are not processing further. This is also completed. Again 10, 3. Again 3 is already processed. We are not processing. Okay, so we got the priority queue empty. At this point we will stop. And return the answer. What is the answer? This is the answer. This is the smallest distance, the shortest path from the source node to each of the node 7 and 6. Okay, I hope it's clear for everyone. Now let's check the code, how we can code this. So these are the basic points we have written. Okay, first the source node we will push in the priority queue, then we will be checking. Basically we will be popping out and then checking, right? Popping out, then checking if it's visited or not. If it's not visited, then we will check the neighbors of that, calculate the sum as we did here, right? For each of the node. for each of the neighbor. Then we will check if the calculated distance, the sum, this is distance basically, and what is the distance formula? This was the distance formula. If the calculated distance is smaller than the current distance, okay, that means the already having distance. Let's say earlier, initially we will be having what? Infinite for all of the nodes. Okay, so if the calculated distance is smaller than the current distance, then only we will update this, update the value of the distance and push it in the priority queue, in the min heap. Correct? Push it, then again repeat the same step, pop it out, check the neighbors and calculate the distance, push it in the neighbor after this condition. Okay, this is the basic steps. Let's check out the code. So this is the main method. Basically we are having the adjacency list, right? List and list of list, and we are having the pair class. What is in the pair? See, in the pair we are having node, we are having weight. I already explained this part. In the priority queue we will be pushing the pair, right? We are pushing what? We are pushing the distance and the node, right? So that's what we will be pushing, and we will be calculating on the weight, on the distance, right? Thus distance is basically the weight. Okay, so we can also write it like this, node and the distance, anything we can write. Okay, so this is the pair. We are having node, the value of the node, and the weight, the distance. Correct? So this is how we created the adjacency list of the pairs, and this is how we are creating the pairs. If you see in the diagram, in the graph, what we are having, we are having the edges from 0 to 1, the weight is 2, right? If you see here, we are setting the list for 0, right, and adding it the pair. Pair is what? The pair, the node value and the distance. Correct? So this is how we will create the adjacency list, and this is the bidirectional, means we are not having the direction, so we will be setting for both the nodes. Let's say from 0, this is from 0 to 1, and this is from 1 to 0. Correct? And same for this, from 0 to 2 we are setting, the weight is 4. If you see here, from 0 to 2 we are having weight as 4, and vice versa from 2 to 0. Same with other nodes, and we are calling this Dijkstra method. In the Dijkstra method, what we are having? First we are creating the distance array, the result. Okay, this is the result. Okay, then we are filling the values with the infinite values. Okay, infinite values. Correct? And we are setting the source distance 0. This was the first step, if you remember. Okay, now starting with the priority queue, we are having the priority queue and we are having the pairs in the priority queue, and we are comparing them on the basis of the weight, right? We are calling this comparator, comparing int, and we are comparing on the basis of weight. Okay, we are having the variable weight, the distance basically, so it will give us the minimum distance node first. Then we are adding this root, that is the first node, the source node in the priority queue. Then we are starting the priority queue, starting accessing the PQ, the nodes, right? And we will stop when our priority queue is empty, when we traversed all of the nodes. Correct? So we started, we will pop the first element, the smallest element, right? Smallest will give smallest distance node each time, right? Each time. Correct? And this will be the current node. We will fetch the node and the weight from this, right? Weight and the node. If you see here, after popping out, we are having these values, right? After popping out, we are having these values. This is what? This was the weight, and this is the node, and we are using this weight in calculate the distance. Here we are using this weight, basically the distance formula, right? So let's copy this distance formula. Where is it? here it is. Okay, so after that, after fetching the node and the weight of that node or the distance of that node from the source node, right, we can say distance from source to current node, right. We will traverse all of the neighbors, right. We will start the for loop and we will be using this adjacency list to get all of the neighbors, right. Adjacency list will give the list of the neighbors, right. If you see here, we are adding the edges. For 0 we will get 1, we will get 2, right, and for 1 we will get 0, we will get 2. Okay, and yes, that's it. 1 and 3, this is basically 2 and 3. Okay, yes, correct. Okay, so this is how we will get the list of neighbors using the adjacency list. After that, what we are doing, again we are fetching the node and the weight of the neighbor, right. After that, we will apply this formula. Which formula? This one, that is distance of v is the current node, the neighbor, okay, this is the neighbor, and the distance we are calculating, right. Distance of u, this one, the current distance, okay, not the current distance, the weight, yes, distance of u, and what else, the weight between them, right. So this is the formula, distance of u. So that's what we are calculating here. See, we are calculating distance of u plus weight. Okay, now distances of u is this distance also, the current distance, we can write it here also. Okay, the current distance, same here, both are same basically. If we are setting this, if we are getting this current distance, before this we have set it this value also, right. If you go above, we have set it the distance of the source as 0 and we are pushing this in the priority queue, correct. So both are same, so that's it, and we are checking this condition. So what was the fifth point? Fourth point is we are checking if the calculated distance is smaller than the current distance, then only we will update and push, right. So that's what we are checking here. If the calculated distance is smaller than the current distance, right, this is the case, this is the if condition, then only we will update the distance. We are updating it here and we are pushing it, correct. So that's it, this is the simple logic. Okay, and that's how we will process each and every node. Let's run this. So we are getting the shortest distance. If you see our result here, what was the result? Here it is, from 0 to 0 it will be 0, yes, it's 0. For 1 it's 2, for 2 it's 3. If you see here, for 1 it's 2 only, for 2 it's 3, and for 3 and 4 it's 7 and 6, same as we are getting here, correct. So try to code it by yourself once. This is simple, these are the simple steps. Remember these steps, then you will be able to code it. Simple steps, right. And what will be the time complexity here? So the time complexity will be like, for this while loop it will take of v, right. What is, let's say o of v, correct. The v is the number of nodes, number of vertices, okay. And for this poll operation, now the priority queue will take log of, it will take log of v, okay. Time complexity for the poll and the push operation, correct. What else, we are having this for loop. What will be the time complexity of this? We are accessing the neighbors, okay. The overall complexity will be the e will be the number of edges, correct. And what else we are having, we are pushing this, right. Pushing this will take log of v. So the overall time complexity, we can say this v log v for this one, correct, plus e log v, correct, for this one. Now we are adding this because this will be the, this o of v will be the overall after adding, right, after adding each and every node and the neighbors. So this will be the time complexity of Dijkstra algorithm. So that's it from my side. This is the easy concept. Okay, I explained you can try it by yourself. Just few steps are there. These are the steps. Okay, and there are some similar questions to Dijkstra algorithm. You can try this. You can find the link in the description with this notes and the link to the questions, the Leetcode link. So thank you guys.